Hi everyone and welcome to this new video. Okay, so today we are here to talk about QFT, quantum field theory, and let's start. Okay, perfect. Today we are here to talk about quantum field theory, and we are going to talk about Lie theory. So today, the spatial linear group and the representation theory. So last time we've seen the thinking diagrams, and for example, AL. Okay, so AL, BL, CL, DL are the algebras, and in particular, AL is the spatial linear Lie algebra. Is the Lie algebra of a particular group called the spatial linear group. And today we are going to study it. And so let's start with the analysis, with the studying of this particular group. Okay, perfect. So this group is called Spatial Relativistic Group Group 2, and it's a group with particular properties, and it's very important in physics. In fact, it's called the Spatial Relativistic Group. Sorry, relativistic spin group. Okay. So this is the third lesson on QFT, but in the second part of the second lesson about QFT. So in the third lesson, in the real third lesson, we're going to talk about symplectic geometry, and so the Lagrangian formalism and the Hamiltonian formalism in quantum field theory, or in a classical theory, in a theory of a point, and so on, of the motion of a point. Okay, perfect. So AL, the SL2C algebra. Okay. Definition of the spatial relativistic group of the spatial linear group. So definition. Okay, what is SL2C? Okay, SL2C. So C is the complex field. It's the set of every matrix of this kind. A, B, C, D. In C, choose 2. Okay, and so this is C4. C4, such that the determinant of this matrix, so the A, B, C, D, is equal to 1. This is the spatial property. What does it mean? I have here the letter S. Okay, this means that the determinant of this matrix is equal to 1. Okay, this is the spatial property. Then I have linear. I have 2, so 2 for 2. So I have 2 matrix of this kind, 2 for 2. And on C. So this means that A, B, C, D are complex numbers. Okay, perfect. Okay, now this group is a Lie group. So in the last lesson we talked about Lie groups. We talked about Lie groups, and we've seen that a Lie group is a smooth manifold with a group structure. Okay, so I have, for example, a differentiable smooth with a group structure, and so I have that SL2C, since it's a Lie group, is a set, of course, is a topological space, is a topological manifold, is a differentiable manifold, and so is a Lie group. Today I'm going to show just the second property. So of course I have it's a set. Okay, it's a set of matrices, and the second property is that it's a topological space. So I'm going to give to this space. Give to this space a topology. Okay, perfect. So the second property, it's a topological space. Topological space. So I have a set, the set SL2C, with a set of opens over the manifold, and this set is the topology tau. Okay. Perfect. So now, sorry, you could. This is a live. This is a live, but this video wanna be a particular lesson about quantum field theory. So this lesson is for somebody that is interested in these topics. Okay. But I know this is a live. But this video wanna be another thing for people that are interested in this topic. Okay, so it's a topological space SL2C with a topology tau, and now perfect to construct the topology over this set. How do I do? So I have what? I can take this set. So B R zeta, and this is the set of every y and complex field such that this is okay. Perfect. What does it mean? This I have a particular type of circle of this kind. So here I have theta, for example, and so I take here this. Okay, I take this. And if I take this circle, this is zeta, this is R, okay, and so I take every point that lies within this circle, okay, so this with accept to the circumference, okay, this the boundary with accept to the boundary, okay, perfect, and so I take this set. Okay, so this is a way to construct a topology over the set SL2C to show that SL2C is a topological space. Okay. Perfect. And so now I can define a particular topology tau on C. Perfect. And to define this topology, I can take these opens tau C for tau C. So I have this thing for tau C, and so on is equal to tau C for C, for C, for C, and so on. Okay, so I can construct a topology of this kind by the multiplication between these elements. Perfect. And so now attention, because I have that SL2C is a subset. Is a subset of what? Of C4. In fact, I have the set of all matrices in C4 such that the determinant of this matrix is equal to 1. Okay, is equal to 1, and so I have what? I have that this set hasn't in here hasn't in himself everything every matrix in C4, just a matrix with this determinant. Okay, so SL2C is a subset of C4, and so I can construct so this is for example tau. This is tau C. Okay, this is a topology. Tau C is a topology on C. And so, in this case, I have that I can define, if I have, for example, this topology for C, C, and so on. In this case, I have that topology as defined as, for example, I have so this multiplication tau C for C, and so on. Perfect. Of course, a topology in SL2C. Okay. Perfect. Now, a particular thing. This set to be a Lie group must be a topological manifold, a smooth manifold, too. And so today I'm not going to show these requirements, but you can think about how to show this, how to show that SL2C is a topological manifold and a smooth manifold. How? Okay, now of course I have a Lie algebra too. Do you remember what is a Lie algebra? Lie algebra is the set of every left invariant vector field endorsed by a Lie bracket. Okay, so I have a group G. Lie algebra is the set a couple of a set. This set is the set of all invariant vector fields on the manifold G, and then I have the commutator, the Lie bracket. Okay, perfect. And of course, this function, the commutator, is a function of this kind, LG for LG to LG. And of course, this function must satisfy some particular properties, and I show you these properties in the last lesson. Okay, so for example, the Jacobi property is the most famous property that this function must satisfy. Okay, perfect. And so now I have a particular thing because there is a particular theorem, there is an important theorem that says what? Says that I have a particular isomorphism between the Lie algebra L and the tangent space over the manifold to the identity E. So to the identity and element. Okay. This is a particular theorem. Why? Because thanks to this theorem, I can resolve many problems about these topics. For example, find the generators of a Lie algebra, and so on. Because of course, if I have that, sorry, a moment. Okay, if I have that. If I have a manifold, okay, and then I have a manifold with a group structure, so it's a Lie group. And then I have a tangent space to the identity over the group. For example, here, okay, I have that this space is isomorphic to the Lie algebra L of G. Okay, perfect. And for example, in the case of SL2C, so this is a Lie group, the Lie algebra, I can write the Lie algebra of this group in this way, SL2C. So this is SL2C, okay, and then I have the Lie algebra SL2C, okay, of the group. Perfect. And now, so in this case, I have the tangent. In this case, of course, the identity map is 1, 0, 0, 1. Okay, here of SL2C as isomorphic. Okay, is isomorphic to the Lie algebra SL2C. Okay. Here, okay, SL. Perfect. Okay, now, okay. So in this case, I have what? I have that, of course, on the tangent space, I have vector fields. Okay, vector fields, and so I have the theorem is this. I have an isomorphism with a Lie algebra. But attention, please, because here I have this symbol, here I have this other symbol. So two different kinds to write the commutator. But this commutator is equal to this commutator. Pi is equal to 3. Okay. So this commutator is equal to this. No, it isn't. It isn't. Why? Because here I have vector fields. Okay. Here I have tangent vectors. The tangent vectors can be vector fields too, of course. But in this case, I have for the definition that here I have vector fields. In fact, the Lie algebra is the set of all invariant vector fields. Left invariant vector fields. Okay. And so, how to define this commutator? Defining another commutator. For definition, okay, it's a definition. Attention, it isn't a proof, but it's a definition, a recall. Okay, because this is a brief lesson about the Lie theory. Okay, so I can do a recall. I have what? I have that. This commutator of this kind, okay, from TEG for TEG to TEG, okay, this commutator of this kind, of course, in this case, I have the group is the SL2C. Okay. Okay. What is a commutator? A commutator, for example, this AB. Okay. It's a particular function of this kind, and I can say this is this particular multiplication, AB minus BA. Okay, because of course in this case we can of course we can R over an abelian group, and so in this case I have that it is equal to 0. But if I have an abelian group, I have a commutative algebra, so a commutatively algebra, and so with respect to some property, for example, is if the for some operation, because if the group operation is a multiplication, I have that the commutator is equal to 0, and the Lie algebra is a commutative algebra. Okay, but AB in this case are elements of the Lie algebra of the group. Okay, and so are vectors, are particular kind of vectors. So now, but I have two different kinds of commutator. This commutator here, there is a function from TEG for TEG to TEG, and then I have this other commutator. There is a function from SL to C for SL to C. Of course, the Lie algebra. I have vectors SL from SL to C. Okay, and I have that the commutator. This is a definition. Okay. This commutator is equal to what? Is equal to the commutator, the normal commutator, I can say normal commutator, LG acting over A, LG dual acting over B. Okay, we've already seen the definition of this map. This map effectively is an isomorphism. It's a particular isomorphism, and in this case, I have my function LG dual is a particular function of this type, of this kind. Of course, this map is induced by another map that is the normal isomorphism LG, and so this is the pullback of the original map, and I have this thing THG, for example, to T 2G, see, yeah, 2GHG, where H is a point of my manifold. Okay, so I have the tangent space to the element H over the manifold. And so in this case, I have this, the commutator is equal to this commutator. Effectively, this is an isomorphism in a tangent space. Okay, perfect. Okay. 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 I have that Lie theory is useful in every branch of physics, I think, because I have that, for example, in the quantum field theory, an example is in quantum mechanics. For example, in quantum mechanics, I have that every state of particles change through a particular operator called unitary operator, and this operator is a particular representation of a group called U1, that is a circle. And so in quantum field theory, I need a representation theory. There is a branch of Lie theory, in this case representation of Lie groups and Lie algebras, and because this These representations are transformations, okay? And I can have groups of symmetries of transformations too that act over something. And it's very important in physics, the invariance concept. And so, for example, the diffeomorphism group, so a diffeomorphism acting over a Lagrangian, and the Lagrangian is invariant under these transformations. So in this case, I can be in a gravity theory, in a theory that describes the gravity field, for example. Thanks. Luca, why is an isomorphism? What this? LG? Oh, you can show this. In fact, this is an injection, a particular injection, and you can show this. There is an isomorphism. Until second declination. Okay. I think the term in Italian, in English, is declination. I think. I don't know. Second declination. Okay. Perfect. So this is the way to define this commutator. Okay. Perfect. Now. Now, another particular thing is this. I have this a theorem that says that there exists an isomorphism, and you can show this too. Okay, this is a particular theorem. If you wanna, we can show this theorem. I can show you the proof of this theorem, this particular theorem, but it's very long. So if you wanna see the proof, I can show you the proof. I can show you it. So LG. So there exists this isomorphism between the tangent space to the identity of the group and the Lie algebra of the group, of the Lie group. And in this case, I have the Lie algebra, for definition, is a subset of the set of all sections on the tangent bundle. A section. What is a section? A section is a particular function that take a point and takes a point and gives a vector. So I take this point, and this function gives me a vector. Okay. So if I am over this manifold, I have a point, and then I take the tangent vector to that point. Okay, a tangent vector. So this is a section such that the projection, the canonical projection composed with the section, is equal to identity map over the group, where I have that P is the inverse, so I have from the tangent bundle to the group, and identity map is this kind of map. For example, I take an element G, and this map gives me the same element. Okay. So now, so this is the set of all sections. Perfect. The set of all sections, and an example of Lie algebra is this: the set of all sections, the gamma set. Okay. Perfect. Now, now, so this is the principal definition, okay? Definition of the set as to C. Okay. Now, so the dual map of this kind, A, B, C, D, dual, okay? So this is an element of the group. In this case, I have SL2C, okay? Acting over of the basis of the group. In this case, I have, sorry, of the basis, I have the derivative with respect to xi over this. What does it mean? Attention. Attention, because in this case, so I show that this particular commutator is equal to this. Okay. Perfect. And now I have that. I take this element. Okay, this element is an element of the tangent space to identity. Okay, and now I take the basis of the tangent space. Okay, so the basis of the tangent space. So this is the basis. Here I have, in fact, the identity element, and now. So I can choose a particular basis for my tangent space of this kind. Of course, we can see this in a normal course of differential geometry. And now I can show this. This is equal to what? This is equal to this A, okay, 0 B, okay, minus B, 0, sorry, A0, okay, C, 0, 1 plus BC over A. Now I'm going to explain this with some example. And then I have derivative with respect to M in the ABCD. Okay. So this is another definition, but I can show this. So I take if I calculate the action of a map of this kind of some vector for definition of this dual map, I have this. What does it mean? An example, okay? An example in my in my case with this group. So to see some examples, we must see this definition. Okay, I have the commutator. So this is element of the group. The basis of my tangent space. Here I have, for example, AX. I don't know. I can have what? I can have an index M. Okay. And so I have M 1 0 0 1, and this is equal to what? For the last definition, acting over a function f for every function in a particular class. Now I'm going to show you which is this class, which is this set. Okay, is defined as what? The commutator L A B C D dual to what? To this X I 001 L A B C T dual. Okay, and here I have AX M 1001. Okay, acting over F for every F lies within this class SL2C. Okay, now so I have here these two indexes, I and M. In the case of my group SL2C, I have a particular group of dimension 4, and so I have what? I have the I can take this I can take this commutator here. So I have ABC. Okay, so ABC is what? I have A is equal to x1, B x2, for example, C is equal to x3. Okay, perfect. And so I can define, of course, I can define the vector. I can define, sorry, the commutation relations. Okay, and so I have from the definition the first commutator. Oh, the first commutator of this kind over F. Okay, so this is what? This is equal to another commutator. So now I have the dual map LG. Okay, LG dual. Yeah. Okay. The big error. What? Which error? And I don't think so, because I can see the. I can see what you see, and I see equations that I write on it. So it's strange. I see what you see, and so it's strange. It's very strange. I don't know. But I don't think so. I don't think so. Okay. So now what I have? I have of course the first line. Okay, so A, B, C for these, and so in the first case I have A minus B A B plus, because here I have plus. Okay, so A for A minus B for A B for plus C for AAC. So plus C for so plus C for AAC. Okay, perfect. The second part, I have the second line, so 0 and 0, so it's just the second element, and so good evening, Albert Einstein. Okay. and then I have A, so I have A for A, B. Okay, because of course is the second element for A, so because B is the second element. Okay, this is the first commutator. But of course, okay, acting over a function. Of course, now I can add the definition. I have, of course, A for this minus B for AB plus C for AC, F. Sorry, this for this AB acting over F minus AB acting over this. Okay, this is the definition of this commutator. Now we can calculate this. Good evening, Gaetano. We can calculate this. Okay, I have this minus this, and this is equal to what? I obtain this result. I obtain, so we can easily calculate this part and obtain what? Obtain this thing. 2 for AB, of course 1, 0, 0, 1 over F. This is the definition. Okay, sorry, this is the result. Okay, and so do you see what I am writing? Do you see what I am writing? The second commutator is A. Now we can do what? A, and then A, C. Okay, and this is equal to what? Here I have so the second the first line, so is equal to this, and I have A for A minus B for B plus C for C, because I have this line that is this line for this vector. Okay, this is a vector of this kind, A M, and so this is AM is A1, A2, and A3. Okay, perfect. And so here, okay. Then the third line, C, and in this case I have B for A 0 plus 1 plus BC A C. Okay, so this is acting, of course, acting over an arbitrary function that lies within this class. Okay, this set of function. Okay, acting over function. Okay, so here I can apply the definition, the normal definition, the non-rigorous definition of a commutator. So a definition used to calculate, the value. I find it boring. Okay, sorry. I'm sorry for this. But I'm happy that you see what I am writing. Okay. And so now, so this is the commutator, and the value is so applying the definition is equal to I think, okay, so I have A, B. You can, if you wanna, you can calculate these two, okay, like an exercise. So how to calculate this commutator. But I think the result is oh oh I the result is minus 2 minus 2 AC over the identity. Okay, perfect. So the result is this. And now I have the last commutator, and so I have here, okay, the last commutator. I have, for example, I have AAB, okay, AAB, AAC, and this is, okay, the same definition. In this case, I have the second line, and I have A for AAB, okay, and the third line, the third column, and this is B for AAA plus 1 plus B, C, AAC, acting over F. The result in this case is A over 1001 F. Okay. So this is the commutation relations. I have the first commutation relations 1, the second 2, and the third. Okay, so if I have this commutation relation, I have so the definitive commutation relations are the first commutation relation 1. I have x1 x2 is equal to, I have 2 x2. Okay. So this is the first commutation relation. If I have the, so what is x1, x2, and x3 are the generators of my Lie algebra. Okay, then of my Lie algebra of SL2C, for example. Okay. So 2, I have the commutation relation between x1, x3, and this is minus 2 x3. Okay, and then I have the third commutation relation 3, and is x2 x3 is equal to x1. Okay. Perfect. So in this case, I have these are the commutation relations between the generators of my Lie algebra SL2C. Okay, so SL2C. And so in this way, I can calculate the structural constants of my Lie algebra SL2C, of the Lie group. So I have the Lie algebra of a Lie group. Perfect. It's totally wrong. This is totally wrong. And it's a bit crazy, just a bit. Right, this is right. This is right instead. Okay, so this is the structure. So this is the commutation relation between the generators of my Lie algebra. Okay. Now, so I can calculate, of course, the structural constants of my Lie algebra, and in this case, I have that my Lie algebra is SL2C. Okay, SL2C is a semi-simple Lie algebra. Yesterday we've seen semi-simple Lie algebra. Okay. Perfect. So we've seen the semi-simple Lie algebra, Ln, for example, and if a Lie algebra is semi-simple, I have that the Killing form Hij is non-negative definite. Okay, perfect. Okay. A little remark: calling A instead of T. You're right. Yeah, it's right. Thanks for recalling. Thanks. Sorry. Thanks for remarking. You're right. Trasformata di Fourier. Fourier transform. I think tomorrow or Saturday. I'll talk about it in the course of functional analysis. Okay. Perfect. So this is the final part about SL2C. This is the conclusive part. Okay. Now we can talk about representation theory. Perfect. Before this, sorry, but I have to go to drink something because I need a bit water. So I'm going to drink. So wait a second. I'll be back soon. Okay, wait a moment, please. Okay, here we are, and so let's continue the teaching about representation theory. Okay. Okay, so representation theory. First definition. First definition. Okay. Let LG LG the algebra, so let LG be the algebra. Okay. And then so our representation of this. So now we are going to find out the representation of a Lie algebra as a different thing from the representation of a Lie group. In fact, I have the representation of this LG is a linear map of this kind. Rho from LG, so linearly, to a family of endomorphisms over over an arbitrary vector space. This vector space is called representation space. So what does it mean this? This means that a representation of a group of, in this case, of a Lie algebra, can have more than one representation, because I have this arbitrary vector space, and I can choose the vector space. I can choose a vector space to make some spaces arise. Okay, for example, we can see the example of SO3. Okay, the spinorial representation is a particular representation very useful in the branch of quantum mechanics, quantum theory, and physics, in theoretical physics. Where I'm now studying, for example, I'm chatting with friends. I'm calling some friends. I'm playing piano. I play piano and these things. But in this period, that we are at home, and we must be at home. Sorry, to come. Okay, and so I in this period that we must be at home. In my free time, I chat with my friends. I call them. For example, when I don't study. Okay, perfect. Sorry. Okay. Do you like video game? I'm not a mister. I'm not a mister. I'm a boy. So you can call me Gabriele. um. So I hope you don't do this only for impresario or to me. No, it's the roast thing. I think it's the roast thing doing this, because we are talking about mathematics. This is mathematics, and doing this is offensive with respect to the mathematics. So absolutely no, absolutely not. What kind of music do you listen to? I love classical music. I love for example, Ludwig van Beethoven, Chopin, Mozart, Liszt. So I like listening to this kind of music. No, I don't know. I don't know it. So I'm going to research. I'm going to search it after the live. Okay. Okay, so a representation space. This is a representation space. Now, I have an important. I have an important property. This representation, this kind of representation has a particular property. Rho of this is equal to this. Okay. Of course, in this case, I don't have any vector fields. In fact, this rho of A is an endomorphism over V. Okay, it's an endomorphism over V. So this function takes a vector fields and gives a particular type of function, another type of function that is an endomorphism over an arbitrary vector space V. Okay. How old is he? I'm 13. I think because before these topics there are many things, and it's very difficult knowing everything about it. So you must study other things before to arrive here. And Nikola Tesla, yeah, it's I see your profile photo, so I can think that you like him. Yeah, it's he was a great scientist. Okay, so now I have in this case so the commutator of this kind as is this endomorphism for endomorphism over V. Okay. Excuse me, Gabriele, I have a question. Could you tell me how you started? Okay, I started learning. I used to learn it. I used some PDF because I think there are many PDF about it online, and so I just use them, and of course I've not finished to study it because LaTeX I started studying it. I don't remember. Wait a moment. Sorry. Okay, sorry. I began to study it 1 year ago, so I don't know many things about it. Okay, sorry, a moment, and we continues. Okay. good job, good job, and thanks, Spider. So okay, and so this is a commutator. Okay, this is a particular type of commutator. Now, an example of representation. Take just the SL2C group. Okay, so the S, in this case, the SL2C algebra, and I have the commutation relation. Yeah, x1, x2, 2, x1, then x2, x1, x3 as minus 2, here I have 3, and then x2, x3 as x1. Okay, and so the representation row of x1, for example, is what? Row of x1 is 1, 0, 0, minus 1. Row. So this is a particular. This isn't the unique representation of my Lie algebra. This is an example, but I can have more representations. X2, for example. I can have 0, 1, 0, 0, and row x3 is equal to 0, 0, 1, 0. Okay, and of course, to show that these three objects are representations, I can show that they satisfy this property. Row of this commutator is equal to this. Okay, and if you try showing this, if you try to show these, you obtain the result that these functions are representations of my Lie algebra, SL2C in this case. Okay, perfect. So I have what? Here I have 1 plus minus 1 is equal to 0. 0 plus 0 is equal to 0, and 0 plus 0 is equal to 0. So this means that trace of every representation xi is equal to 0, and so the property is that I have the property of this is I have what? I have row of SL2C is what? As this matrix alpha, beta, gamma, and which other leader? I think maybe delta. Okay, such that alpha plus delta is equal to 0. Okay, this is the example. This is the example this is an example for SL2C. Another example, so this is one. The second example is the Lie algebra SO3 over R. This is an important group in physics because it can be shown that every matrix that lives within this group is a rotation matrix, okay? And so the Lie algebra of the group, this is not the group, this is the Lie algebra of the group big SO3 over R, okay? And I have the commutation relation. In this case, I have the structure constants are the Levi-Civita symbols. Okay, so in the case of SO3, I have the Levi-Civita symbols, and I have xk. Okay. Okay. Perfect. And so, for example, I can calculate the killing form. I can calculate the killing form, but I want to show you a representation of this group, rho. Okay, here we are. Sorry for the problem. Okay. Perfect. And so, a representation for my space. Okay. A representation for my space. I have. So sorry, a moment, please. I have. Okay, so I have rho of x1 is equal to 0, 1, 0, minus 0, 1, 0, 0, 0, 0. Rho x2 is equal to 0, 0, minus 1, 0, 0, 0, 1, 0, 0, and rho x3 is equal to, sorry, here, you can write here. I have rho of x3 is equal to 0, 0, 0, 0, 0, 1, 0, minus 1, 0. Okay, so these are the representations of my SO3, a group of representation, because I can have other representations. For example, another type of representation for my Lie group, Lie algebra SO3 is the spinor representation. The spinor representation is a representation that is from SO3, of course, R. But in this case, the representation vector, space, the representation space is C square. So the family of all two for the family of a particular matrix over C4, C2. Okay, and in this case, I have the rho of x1 is equal to 1 over 2 for sigma 1, sigma 1. Okay, what is sigma 1? What is sigma 1? Sigma 1, wait a moment, rho of x2 is equal to 1 over 2, sigma 2, and rho of 1 over 2, theta 3. Okay, in this case I have that sigma I are the Pauli matrix. Okay, the Pauli matrices, sigma 1, sigma 2, and sigma 3, and they are very important in quantum mechanics, for example. So this is the spinor representation: rho of x1, rho of x2, and rho of x3. Okay. Of course, I can have a trivial representation. I can have a trivial representation. Thanks Rappetto. Lo dico un attimo in italiano, ne parliamo in un altro video poi, perché ho fatto già dei video in questo. Benvenuto quindi nella ciurma, diciamo, di YouTube, e quindi poi ne parliamo in altri video, ma ho fatto già alcuni video su questo. Ok, torniamo in modo inglese. Ok, so I have these representations of my group. Okay. Okay. Perfect. Now, definition. Definition. Okay. Okay. So I have the definition. A representation rho from L to my family of endomorphism over V. Okay, is called as reducible. I have attention. I have reducible. So as reducible if there exists okay, if there exists a vector subspace U of V, so of the representation space, such that I have for every A lives within L, and for every U lives within U, I have rho of A V lives within this vector subspace. Otherwise, we can talk about irreducible representation. Okay, perfect. So if I have this, okay, perfect. Now, if I have, for example, the vector representation of the Lie group, sorry, of the Lie algebra SO3. Okay, so the vector representation is this, and if I have the spinorial representation, this. Okay. I can construct another representation that I call rho. Okay, sorry, rho is of this kind. I have endomorphisms over R3 direct sum C squared. Okay, and this kind of representation is this rho of A, so of an element of Lie algebra, is this as an isomorphism. An endomorphism of this kind. I have a matrix block matrix rho vec A and rho spin A, and so I have here these two matrices, and here I have the zero matrix. Okay. Perfect. So here the vectorial spin, the vectorial representation, here the spinor representation, and here 0 and 0, so the zero matrix. Okay. Of course, in the first case, I have three matrix. I have 3, 4, 3. And here I have here this. Okay. Perfect. Now we can talk about Casimi operator, for example. The Casimi operator. What is the Casimi operator? So definition of the Casimi operator. So first, if I have a representation rho from L to a family endomorphism over V, of course, this is the definition. I can define a rho killing form. Okay, a rho killing form on L of this kind. Okay, I have key rho. Okay, from L for L to C. And I have what? I have that if the first killing form is the trace of a composition of two adjoint maps, in this case the rho killing form is this, as defined as the trace of the composition of these two maps. Here we are. Okay, perfect. Now, we can define the Casimi operator. The Casimi operator is this operator, so define the Casimi operator as an operator of this kind of omega rho from V to V is linear, and is defined as the sum from I is equal to 1 to dimension of L row of xi composition row of ki, where here x1 until x dimension of L and Q1 until key dimension of L is these two x1 until x dimension of L and these are two bases of L, okay, such that I have such that the row killing form of x I key j is equal to the Kronecker delta ij. Okay, so this is the killing the of course this is an endomorphism, okay, omega rho. In fact, I have the commutator between the Casimi operator, so it's an isomorphism because the commutator takes two endomorphisms over a vector space and gives just only one endomorphism over the vector space, and so here I have the commutator between the Casimi operator and the representation. A representation of my Lie algebra as equal to 0. Okay, I can. I have what? There is an important lemma. There is an important lemma, and this lemma is called Schur lemma. The Schur lemma, lemma di Schur. Schur's lemma. If rho is irreducible, I have that the Casimi operator can be written as the multiplication by between two elements, C rho and the identity map on the vector space V, where C rho is the quotient between the dimension of L and the dimension of V. Perfect. So this is an example. Here we are. Okay, and now so this is the definition of this is the Schur's lemma. Perfect. Now I have, so the Schur's lemma is very important. Okay, it's very famous. And the last definition of this lesson is the representation of a Lie group G. So definition. I have what? I have that. Let G with a block operation, with a group operation, be a group and a representation as a linear map is a linear map of this kind. rho to G to GLV, where GLV is the general linear group, okay, and V is the representation space, and I have that GLV as the set of all endomorphism over the V over V, such that the determinant of sorry, here I can write R, for example, the representation R is equal to 0. Okay, and I have that R of G1 for the operation, the group operation, RG2 is equal to RG1 G2. Okay, perfect. So today we've seen what? We've seen the SL2C group, the SL2C algebra, the representations of a Lie algebra, and the representation of a Lie group. Okay, I can say that a representation, I think, and physics is very important representation theory of Lie algebras, but representation of Lie group is very important too. In fact, we met these in the course of functional analysis. So if you have any question, you can ask now because you can do this. And so if you have any question, you can ask about the lesson, of course. Otherwise, I would close it. I'd close it. I'd finish it. I'd finish the live here, I think, because time is arrived. So if you have any question, you can ask about short lemma, the representation of group, SL2C, the group SL2C. No, absolutely not. Absolutely not. I am Italian. I'm Italian. I think yes. I think I can do some video about this topic. Yeah. I've already done some video about quantum mechanics, but I've talked about quantum mechanics with a strong mathematical formalism, I think. Strong. Why strong? Because in my course of quantum mechanics, there is many mathematics, many advanced mathematics, and so I haven't talked about the experimental part of the quantum mechanics, and so I can do it. Yeah. Hi, Astro Gabri. 13. I'm 13, and I don't know. Of course, I'd like, but there are many college, many good college, great college to, for example. Normale, the Normale of Pisa, it's an example, but Oxford is a great university. Thanks, Astro Gabri. Thanks. Thanks. Oh, okay, perfect. I write, choose, and eat. I am in the. I am in the. I don't know the name in English. Mm, I am not in the high school yet. But for example, and science, I'll talk about. I'll talk about genetic. Okay. Okay. Why should I take a fake glasses? Why should I take a fake glasses? You can see it. Okay. Yeah, I have some problem. I have some problem when I when I must see something. So why should I take why should I wear hmm, fake glasses? Um, um, I like to study string theory. I like to study string theory and make research in the field of string theory and quantum gravity. But more detail, I think string theory. String theory is my love. Okay, I don't know. I don't know. The fractals are topics that I don't see in more details. So I don't know. Okay, yeah. No, it looks like a bit strange. Sorry, but when I read it, it looks like a bit strange. But sorry. Okay, so I think we can close we can finish here live, and so in the next lesson we are going to talk about symplectic geometry and Lagrangian formalism. So Lagrangian formalism and Hamiltonian formalism for a theory for a dynamical theory. Okay, perfect. And after the third lesson, we are going to start talking about the quantum field theory. With the first lesson will be about the Lagrangian in a field theory, and the fifth lesson will be about the canonical quantization. So see you soon.